Okay, let's have an example here. So where is the gamma of t that we had? Yeah, here is the gamma of t over there. Okay? We can get maybe gamma dot t is 1 and half 0, right? So this is in the tangent space.
Why is it 0?
1 is 0.
Oh, sorry, it's not 0. Negative what? This is 5 over 2, 5t over
10.
no, 10, right? 10 over 4 divided by square root, yeah. This is gamma dot of t, but in fact, I am only interested in gamma dot of 0. Why? Because I'm talking about the tangent space at the point. The point, what's the point? The tangent space at P, okay? P was at time 0. So I'm gonna get gamma dot of 0. This is what I meant, 1/2 and 0. And this is in T, P, M, okay? We call this a tangent vector in the tangent space. It's a velocity vector of some curve passing through the point. Nothing fancy. Any questions so far?
What's that third term in the gamma
Yeah.
dot of t?
Negative 10t over 4 divided by square root 1 minus Laplace, or the square root that we have. I mean, it would be 0 because you gotta put t 0, so I didn't. Okay, any questions so far? Any question? Please, I mean, if you have a question, just bring it. We can discuss more, that's fine. I'm gonna jump a little bit. I'm gonna say the differential geometric view. I mean, everything now is geometry. Where does the differential come from? It is just a flavor of it. When you have a V in the tangent space, V is like this maybe, or V1, V2, V3. Okay? Well, we write them in bases, V1, E1, V2, E2, and V3, E3, okay? Any questions so far? In differential geometry, please just pay attention here. In differential geometry, our bases actually, they are differentials. Partial x1, partial x2, partial x3. Because tangent vectors in differential geometry, this is maybe the fourth word or whatever, or the fourth convention. In differential geometry, this V as a tangent vector, we always see V's as acting on functions. V takes function, V dotted with F or V of F. V takes function and gives you what? Well, multiply this by a function, any function. You get V1 partial F partial x1 plus V3 partial F partial x3, right? This is nothing but the vector V dotted with nabla F. Okay? Anybody remembers the name of this guy? V dotted with nabla F? V dotted with nabla F? The directional derivative. Directional derivative. So it's the directional derivative of the function f along the vector v. It's how fast f changes along v. Just to make you feel it, here is an ocean, okay? And the temperature changes along the ocean. Maybe the temperature here is 10 Celsius, maybe. Here is 5. Here is 0, here is negative 10 or something, okay? And this thing doesn't change with time. Every time, this is 10 here, 5 here. and I have the flow of the waves of the ocean or whatever river vector. Okay? If I have a particle flows with the river or with the ocean, it will feel hotter as it goes with the ocean, right? Although the temperature itself doesn't change with time, but as he moves, he will feel change in the temperature. Okay? How much is this change? It's exactly V dotted on the line. How much the F here is the temperature function, scalar function. This is the meaning of the direction derivative. How much your function, scalar function, changes along a given vector. In differential geometry, everything is viewed from this point of view. So from this point, please bear with me here, V in TPM actually is viewed as the following. V is a map that takes a function, smooth function, because we're going to differentiate it. So here is smooth, C infinity of M. This is the space of smooth functions of M. Smooth function, and gives you what? Gives you what? Exactly, number. What's this number represent? Is how much this function changes along V at that point, because V is defined on a point only. Okay? I'll do a very simple example here. So I have my V from there, my V is gamma dot 0, is 1, 1/2, and 0. I'll define a function on M, is simply maybe x, z, plus y, plus z squared, anything. So what is V? We write it like this, Vf or V of f. It takes f and gives you something, right? By the way, when a map takes a function and gives you a real element, anybody remembers its name? Takes a function, gives you a number. What's that? We gave it a name before. What?
Function.
Functional, right? This is a functional. Okay. So V of f, what is V of f? This is very easy. You do it in 200A many times. The first component, partial f, partial the first component, second component, partial f, partial the second component, and 0, right? It's very easy. This is 1 times partial x is z plus y, 1/2 here. And you have to, no, this is 1/2, right? And you have to substitute by the point. Don't forget that. 0, 0, 1, my point. Because this vector was defined only in the tangent space of a point. It was the North Pole. So when you substitute, you get 1.5, 1.5. What is this? It's how much this function changed along that direction. Okay? So I'll just take 2 minutes. Give one last example. Any questions so far? We'll finish this. Yes, Mr.
Could you please explain the notation once for C infinity M?
Yeah, sure. This is, you remember C of A and B. What's that? The space of continuous function on this interval. If I replace A and B and put M, so this is the space of continuous function on M. If I put here 1, differential, 2, twice differential, infinitely differential. This is the space of infinitely differentiable, or we say smooth functions on M. Who can interpret this thing? Can you tell me this in words?
The tangent space.
The tangent space of this manifold, whatever it is, I don't care now, it's the special orthogonal, which is interestingly the configuration manifold of the rigid body. I want the tangent space of the rigid body at some point. Let's talk about the identity matrix, right? Because any point here is a matrix. Okay? I want to get that. Well, what characterizes this manifold is any matrix, 3 by 3 that satisfies A transpose's identity, right? So how can I get the tangent space? The tangent space is the set of all velocity of curves. So I will have, maybe here is your space, and I would have gamma of t, that at any t running, it gives you a matrix here, right? And the matrix, since it's here, it has to satisfy this thing. Okay, this is the curve. And I want the velocity of that curve. So let's differentiate this equation to get